Hello, I'm Eric Garcia, and I have permission for you to use this video on Blackboard. Okay, so I'm doing the Unit 3 test corrections, and the first question that I missed was number 3. And in number 3, you're tasked with finding the second derivative of an equation that you found earlier. And the derivative of that equation that you're finding the second derivative of is sine x over cosine y plus 5. So to find the derivative of sine x over cosine y plus 5, you use the quotient rule, and you come out with this expression right here. The point where I went wrong in my calculations was I multiplied dy over dx times this entire expression, dy times the whole top function, and dx times the entire bottom function. Instead, I should have just multiplied dy over dx times this function right here. After properly multiplying there, I was able to get the problem correct, and I was able to simplify it properly. So the process of correctly solving the problem is as follows. dy over dx is sine x over cosine y plus 5. You multiply that times this expression right here, and then you continue to simplify. So the right side of this little addition right here comes out to be sine x squared times sine y over cosine y plus 5. And then in order to add these two expressions, you had to find a common denominator, which is cosine y plus 5. So you multiply this side of the equation times cosine y plus 5 over cosine y plus 5. And then you're able to successfully add these two. When you add them, you get this right here. And then I just brought the denominator of the entire expression out to the side and multiplied times 1 over cosine y plus 5 squared. So I did that. I got the final answer after a little bit of simplification. I got the final answer here of cosine x times cosine y plus 5 squared plus sine x squared sine y over cosine y plus 5 cubed. Okay, so that's the first problem I messed up on. The next problem was 6c, and it said evaluate the limit as x approaches infinity of x squared plus sine x over x squared. And I sort of really overcomplicated this problem by using L'Hopital's rule too many times, and I ended up with a 0 in the denominator, and I guess in the heat of the moment during the test, I just said that it was undefined, and I was kind of out of it. But to properly do this problem, you don't overcomplicate it. You just look at it simply, and you break down this equation right here into its little constituent parts, and you get x squared over x squared, which is 1, plus sine x over x squared. And then if you just plug in infinity, this approaches 0, because as the bottom gets larger and larger, this stays between -1 and 1, so it bounds to 0, and you're left with 1, so 1 plus 0 equals 0, and the limit is simply, 1, not 0, just to clarify. Okay, and the last problem was 8b. Here's the graph of the equation you're given for this final problem 8. And the problem I missed was it said find all values of x for -3 is less than x is less than 3 at which f attains a relative max. Justify your answer. My mistake was that I didn't use the first derivative test to prove or disprove the existence of a local max. Instead, I proved the existence of an absolute max, and I messed up the problem. To prove my point and to get the problem correct, I just used the first derivative test. And the first derivative test for this equation, where I'm proving or disproving the existence of a local max, is as follows. F of x does not have a relative max on -3 is less than x is less than 3. This is because at neither of f of x critical points, which are x equals 3 and at x equals -0.5, at neither of these critical points does f prime change from positive to negative, Because f prime does not change from positive to negative at any of f's critical points on this interval, there exists no local max on negative 3 is less than x is less than 3. Therefore, I've proved that there exists no local maximum on this interval, and I've solved the problem. Thanks. I'm Eric Parziot.